first time that I'm visiting Davis. So excited. So this is a quite informal talk. So some part is work in progress, some part has been already published, so it's nice to hear your feedback. So basically, can I maybe use this as model? Yeah. So basically, for this talk, I want to answer these questions. So I would like to understand with you if there is room left, and what kind of room is left for Z-prime gauge bosons that are quite light. With light, I mean like below 100 GeV or so. And if so, how one can probe them. And in particular, what is the role of the Higgs boson in probing them. Okay, so this is basically the question that I would like to answer for this talk. But yeah, here is a more traditional outline. So first, I would like to show you what is the present status of Z-prime searches at LHC. And then I will present two models that have quite a bit different motivations. So the first set of models are models with an additional U1 symmetry that is producing a Z-prime that is actually kinetically mixing with the Z of the standard model. These theories have been motivated quite a bit thinking about dark matter. So as I will show you a little bit later, basically these models here can accommodate a good candidate of dark matter that is still hidden to direct searches of dark matter and also LHC searches. And so for this set of theories, I would like to understand indeed how to probe these Z-prime bosons if they come from the decay of the Higgs boson that has been discovered at LHC. And then instead, this second set of models are models where engaging the mu minus L tau symmetry. And we see how the Z-prime associated to these symmetries can produce interesting effect in neutrino physics. In fact, these models have been motivated originally by neutrino model building. And indeed, I want to show you how it is possible to probe these models using some neutrino experiments, and also some experiments that have been done at LHC, so in particular the search of this decay of the Z in four muons. And yeah, here is a set of references that I will use for this talk. So here is the reference to this big review about Higgs exotic decays that we wrote that appeared last December in the archive. Then there is a paper that I've done with my collaborators at Perimeter Institute, and then, as I said, there are some work in progress here. So I think I do not have to speak so much about motivations for this Z-prime. We know, and it's always good to find motivation to study something. But we know that these Z-prime models are arising from gap theories, from theories with extra dimensions. We know that if you put these additional gauge symmetries in the framework of supersymmetry, then you can have kind of more natural theories, because you can have, first of all, non-decoupling deterrence in the Higgs mass. So it's easy if you want to get to this 125 GeV Higgs. You can have solution of the mu problem. And then also you can have quite interesting phenomenology, because as we will see in the following, you can have extra handle for neutrino model building, extra handle for model building for dark matter, some effects in G-2 if this guy is coupling to muons. So overall, it seems to be kind of justified to study models with Z-prime. And in general, I would like to see these models as kind of effective theories at a low scale, as we see usually 2x orbit models as effective theories for coming from supersymmetric models. So there have been a lot of searches at LHC for Z-prime. So some searches are looking for the lepton resonances. Here in this plot you see what is the present bound if the Z-prime is decaying to 2 electrons. Particularly, you can look at this band here, this gray band here, that is for a sequential standard model Z-prime. Basically a Z-prime with the couplings that are the same as for the Z of the standard model. see that in this case we are already approaching the 3 TeV or so of mass. Weaker bounds are coming as expected from the searches of Z prime decaying to taus. But still, you see also in this case the bounds are at, for masses headed down 1.5 TeV or so. So it seems that if these guys reactively produce at LHC, so if it couples with full strength to the first generation of quarks, and then it decays to leptons, then it has to be a mass that is relatively heavy. Down here, so usually when you see these plots of the LHC, they stop at 100 GeV. Down here, you have to look at LEP. There are constraints from LEP. In particular, they test couplings with quarks and leptons at the level of 10 to minus 2. So you have to, to think to extend these plots also further, taking into account the LEP bound. And then also there are constraints if these Z prime are decaying to jets. So there are plenty of dijet resonances searching. And in particular here is a nice summary of what has been done in the past and more recently by CMS and Atlas for the search of a Z prime that is decaying to 2 jets. So we see LEP bound, Tevatron bound, and Atlas bound and CMS bound. And we see that basically if you are thinking about couplings of the order 1 or so, again the conclusion is that we are already probing masses of more than 1.5 TeV or so.
So is that coupling of order 1 or order 1 compared to
so this is the definition and the coupling that you have to take for the Z prime to jets.
Maybe is the 1/6 more or less equal to G prime?
Yeah, roughly, yes.
So really, there's essentially no bounds below 1. I mean, for any mass. I mean, there's the CMS bound, but I mean that's
right.
Or let's say 0.5 for any mass. There's no bound.
Yeah. Apparently so. Yes.
It seems.
I see.
Yeah.
Wow.
Okay, I'm trying to understand that statement because if you said GB equal to 1, then it's very easy to see the Z, right? Because that's the same as the Z at 90. So
right.
Going
But
to
we are
jets,
speaking about
though.
masses, that are already 1.5 TeV or so your cross section.
Well, I was just looking at the region, around 100, where the regular Z is.
Oh.
So is that curve at the low end explicitly cut off above the regular Z?
Yeah.
Well, anyway, it looks like it goes down to maybe of order 100, does it?
Right. Yes.
So I would have said that you could have gotten much stronger bounds if this was a Z with the same coupling as the regular Z.
So
because the regular Z is very easy to see, right? So I would have thought you could have gotten a factor of 10 better bound.
I'm wondering, so you're speaking about this region here, right?
Yeah,
so
right.
below the Z
Yes.
mass.
Yeah.
I'm wondering, so as I was claiming here, so typically when you read lab 2 papers about this, typically the claim is that so they can exclude the couplings at level 10 to minus 2.
Yeah, but I'm talking even about at the LHC. If you had 100 GeV second Z.
Yeah, but this one only couples to quarks, Jack.
Yeah.
So it makes it much harder.
Exactly.
It's buried in the background.
Right.
I
Yeah.
see. Okay. Well,
I mean,
that's
at
what
lab I
hadn't
can agree with you, but
appreciated
LHC, doesn't look good. Yeah.
Okay. Well,
It would be pretty hard to find the Z just in dijet events.
Yeah. I mean, it has to be heavy, of course. Yeah.
okay. Well, maybe it's okay. All right. Okay. Anyway, now I understand. I never caught that. Okay. Continue.
And then, last, there is this interesting search of a Z prime 2 tops, so it's a ditop resonance. These searches are quite more complicated, as you can imagine, it compared to the dijet resonances, because you have to reconstruct tops and then reconstruct the Z resonance, the Z prime resonance. And again, Atlas is setting a bound on this, collection cross-section time branch ratio of these Z prime 2 tops. And so this is the bound, and this is the comparison with the particular model that I'm taking here, this leptophobic Z prime that is, predicting this type of cross-section time branchidation. So again, for this model, you are, putting bounds at the level of almost 2 TeV or so. But yeah, of course, I mean, this depends on the particular model that you're writing down. But what is quite interesting to see that, you are already bounding, you are already putting a constraint on cross sections at the level of a picobarn or 1/10 picobarn. So this is basically the status of Z prime resonances searches. So from here, it seems that indeed, maybe I should not talk about 100 GeV Z prime. But actually, we show you later that there are kind of well-motivated models that are producing Z prime that are so light, but still in good shape with their present searches. And of course, so here I'm speaking about direct searches. Then there are kind of indirect searches, if you want, of Z prime. And this is nothing other than electroweak precision measurement, of course, because this is more or less the state of the art of the global fit of all the electroweak precision observables of the standard model. We see that the p-value is quite good, so we might wonder if there is room for putting in here some Z prime observables that are in principle affecting all these observables for the Z boson and the W boson. So we'll see later what is the role of electroweak precision observables in putting bounds on Z primes that are particularly light. Okay. So this is simply a bit of warming up for Z prime. So let me start with the first model that I would like to discuss with you. So these kinetically mixed Z primes. So they were, and we are, motivated by dark matter. So basically the idea is that you have two sectors. One is our sector, the standard model sector. One is the dark matter sector. In first approximation, these two sectors are not talking. But then there are some interactions coming from these mediators. So this can be indeed some Z prime or some dark scalar. And thanks to this mediator, the dark matter can annihilate. If the mediator is lighter than the dark matter, then it can be produced by the dark matter annihilation. So basically the dark matter can be thermal in these models, but at the same time, since the dark matter is not directly torquing to the standard model, then your direct signals for dark matter interacting with nuclei or LHC or in principle LHC signals for dark matter are quite suppressed. And so basically you end up in having this dark sector for dark matter. They are working well, but then to discover them you have really to look at indirect searches for dark matter. So this is the motivation for having this kind of models. And a lot of attention has been dedicated to models in which you have this additional U1 symmetry with the Z prime, the Z dark, that is mixing with the hypercharged Higgs boson through this kinetic mixing operator. Then, of course, you have the standard model, then some mass term for this Z dark Higgs boson. If you have this theory, then the first effect that you can think of are effects on the Z phenomenology, because as you can see from here, the Z and the Z dark will mix, and then you will have some tree-level effects on the Z mass, it is quadratic in epsilon, and then also you will have effects on the Z couplings to fermions, that is of the same order. So we can ask the question of how much we are constrained on this epsilon simply because of the measurement of the Z properties. You can do this exercise, and basically you can see, so you can draw your constraint in this MZ dark epsilon plane, that is basically these are the only free parameters of your theory. And you see that basically electroweak precision measurements are giving the constraint for epsilon larger than something like 10 to the minus 2 or so. And this constraint here is that is mainly flat, is coming mainly from this three-level shift on the Z mass. So electroweak precision measurements are telling you that this epsilon cannot be that large, so we're speaking about something like 10 to the minus 2 or so epsilon. And then here the constraint, if you approach the Z mass, the constraint becomes a little stronger because here you're also affecting the decays of the Z, so the total width of the Z, the sigma dronic, and so on. So here there are other observables that are also contributing. So this is actually the only region of parameter space that has been probed by LEP with electroweak precision measurements. Then there are all these other regions that are actually quite different experiments. So this region here is being probed by bar. So this is the process that they are looking at. So the production of a Z dark in association with a photon. And instead all these other experiments at lower masses and also this apex experiment are fixed target experiments. So basically what they are looking at is, they are shooting some target with electrons, and then they are looking at the production of this Z dark that is decaying to typically leptons, and then they're setting this constraint. So basically this is the state of the art of the constraints on these kind of models. And what we want to ask...
Just a quick question on the left case, bar, is that the diagram is just some electron exchange with gamma coming out and Z dark coming out?
Right, yes.
Yes. It's just that simple.
Yes,
okay.
yeah. And then, here you are cut by simply kinematic. I mean, you don't reach that much energy because Baba is, has low energy. So.
Right.
Yeah. So the question is if we can do something here. Here it looks kind of more promising because, the epsilon that you are thinking about are at a level of 10 to the minus 2 or so probably it's much easier to, probe here than here. Actually here, if you are interested, there are actually several people at Perimeter that are trying to understand how to probe this region here. And these are other fixed target experiments, like at JLab or Mini-Boon. The idea is the same, that you are shooting some target with either electrons or neutrinos, and then you're looking at the production of a Z dark, but then now this Z dark is decaying to dark matter. So basically here, I'm trying to use some probe, but here there is nothing.
So why isn't there a search from the just producing Z dark, then going to leptons?
Yeah, so this goes back to the second slide or so that I had, that there are searches, but actually they could probe Z dark below the Z mass, only if the coupling to electrons is quite large. It's larger than 10 to the minus 2 or so. So basically, if you do the exercise of putting the bound from direct production at the lab, this bound would lie down here. Okay? It's a little bit weaker than electroweak precision measurements, but yeah, comparable if you want. But there is nothing, beyond 4 or 5 small epsilons. Yeah. So the question is if the Higgs can do something here. And so the Higgs is mixing, is interacting with the Z dark through these diagrams here. So basically, you have some mixing of the Z and Z dark. So basically, the coupling of the Higgs with one Z dark will be linear in epsilon, and instead quadratic in epsilon is the Higgs coupling to Z dark. So you can imagine that you can have some, if this Z dark is light, then you might have some decay of the Higgs into Z dark or intrinsically also Z dark. And this is what we wanted to probe and to see what are the chances to see this decay mode at the LHC. If you look at the decay of the Z dark, so Z dark is actually not stable here. And it will decay promptly to all these guys, so either to jets, charms, leptons, and big quarks, or also neutrinos. Actually, if you look at this branch ratio, you see that summing up electrons and muons, you have something like 30% or so of decay of the Z dark into leptons. So effectively, if you think about the Higgs decaying to Z dark, you will have a 4 lepton signature. So it seems pretty nice to see and pretty straightforward to see. But actually, so since we are considering some extra signature of the Higgs, one might wonder what are the the constraints coming from the study of the Higgs boson at LHC. In fact, you cannot imagine to have a factor of a branch ratio of the level of 90-95% or so to something that has not been studied at LHC, because there are constraints on the Higgs widths. So we were speaking like 1 hour ago or so of this quite cool measurement of CMS. It is a direct measurement of the Higgs width. So basically what CMS is doing is to look at this process, so production of the Higgs, that can be on shell or off shell, and then the Higgs going to ZZ. Okay? So before this public note, only this measurement was available. So it's simply measurement on peak, so you produce an on-shell Higgs going to ZZ star to 4 leptons, and then basically you measure this rate nu in terms of this reduced coupling of the Higgs with gluons, Higgs with Z, and the total width of the Higgs boson. But then actually what CMS also did was to look off-shell. So basically they look at the distribution of events in terms of this invariant mass of the 2 Z's. And this distribution here won't depend only on the value of mu, but also directly on the value of this ratio of widths for the Higgs boson. So basically, to putting together these two measurements, you can extract and put a bound on this width. And this has been done, and actually, as John, you were saying, the bound on the width that has been observed is quite stronger than what was expected. And we are at the level of 4 times or so the width of the standard model Higgs. And this is quite interesting because, as you can see from here, this is kind of model independent. It doesn't rely on some fit that you are doing of the rates of the Higgs boson. In fact, there are also some bounds that are coming from fitting the Higgs properties. So basically what you are doing is to try to fit all the rates that LHC is giving you. And these rates, for example, the ZZ rate will depend on the total width of the Higgs. And then your global fit can give you an answer, a bound on this total width. And this is what has been done. So there are really plenty of global fits for the Higgs rates and widths. And what we can learn is that already branch ratios in something that is exotic or invisible at level of 60% have been excluded by this global fit. It depends, the result depends actually quite a bit on the assumption that you are doing for your fit. Sometimes you can see some stronger bounds at the level of 20-30%, but typically you don't see bounds, stronger than 30%. And even there are projections for the end of the LHC, so 300 inverse femtobarn of 14 TeV data. And you can see that typically you cannot get a bound by more than 10% the Higgs width of the standard model with this amount of data.
So this down here, of course, allows unconstrained values for C sub V, I guess.
Right.
So C sub V is not constrained to be below 1 for this kind of number.
Right.
Is this number also allowing any
Yes, they do.
CV?
I think they do the same assumption that CV cannot be larger than 1.
Oh, this one does assume CV.
Right, right.
But this one doesn't?
I think also this, all the fits that I saw are always assuming that it's smaller than 1. Some fits are assuming that it's exactly 1, but typically,
Well, because we have a much stronger result for, an arc fitting paper if you require CV less than 1 or less than or equal to 1.
Oh, I see.
Then the bound is more like 34% from Higgs fitting.
Right, yeah, so this 30%. Yeah.
And that's at 95%. So
Yes.
I guess I disagree with this Atlas. So, well, maybe it's only Atlas.
Oh, no.
data.
So the 60% you want to
Yeah, right, yeah.
No, the 60% is kind of a cheap fit, if you want, because so the free parameter of the fit in this specific case are only the coupling of the Higgs with photons and the gluons and the total width. That's it. All the rest has been fixed to be standard model. So it's a free parameter fit. So it's a very, very constrained fit, if you want. And doing only these 3 parameter fit, you get the 60%.
I
If you
really
do-
thought that would have been more constraining than a general fit, so I'm confused. I'll have to look at this Atlas thing more closely, I guess.
Yeah. No, I think so. You get more constraining if you put more ingredients in the fit, because yeah.
But you have more free parameters. If you're assuming couplings to the up and down sectors that are free, then
Right.
that gives you, should give you less constrained. Yeah.
Makes sense what you're saying, but yeah,
Because you say this number assumes that the up and down couplings are standard model like.
yeah, the 60%, yes, yeah.
So I don't understand this. Okay, anyway.
Mm.
Okay.
Yeah, actually, also this is the only official fit that I found from the experimental collaboration that is not done by theorists. But yeah. Anyways, this slide was simply to say that even if you are optimistic and you think about the end of the LHC with 300 inverse pentagon, a 10% partial width in something that is exotic won't be probed. And if you think to the number of events, this is a really huge number of events. So this is the number of events for a production of the standard model Higgs with the 10% of branch ratio, and both at 8 TeV and 14 TeV LHC. So the question is if one can do something with all this huge amount of events that in principle could not be really probed by the study of standard model properties. And this is basically, in a nutshell, our motivations to really focus on Higgs exotic decays, to try to understand if there are additional direct searches for the Higgs decaying with something exotic that are not probed in the classical standard model channels. And but coming back to the Higgs decaying to ZZ dark, so we said that the signature that we want to look at is a 4-lepton signature. So we know that there are searches for Higgs going to 4-lepton coming from ZZ star. Actually, these searches are really crucial because they give the most part of the significance for the presence of the Higgs, almost 7 sigma at both experiments. And so what they do is to require 4 isolated leptons, 2 same flavor opposite sign pairs, and basically they call, I think CMS is calling Z1 the leading pair, so the pair with the largest invariant mass, and Z2 the sub-leading pair. And here you can see the distribution of events for Z1 and Z2. So typically you can imagine that for this, the 2 leptons of Z1 are coming from the decay of the on-shell Z. Z2 leptons are coming from, let's say, the decay of this off-shell Z. And of course you will have some extra events if you think about the decay of the Higgs to ZZ dark. So first of all, what we investigated is the on-shell production. So the Z dark is quite light in such a way that both Z and Z dark can be produced on-shell. And so what you do is basically to look at the several beams for this Z2. So now this Z2 pair will come from the decay of this Z dark H boson, that is the lightest, most probably, So basically, this Z2 mass will be the Z dark mass, and these beams here are nothing other than the bounds on the number of events that you can have on the several beams. So you can simply do a simple counting experiment to see what kind of bounds you can have on the branch ratio of the Higgs to ZZ dark times the Z dark and 2 leptons. You see that the bound is already quite strong at level of few 10⁻⁴. And in terms of the bound on the branch ratio of the Higgs into ZZ dark is at the level of 10 to the minus 3.
Do you happen to know whether this plot includes subtracting off the standard model expectation?
Yes, it does. Yeah. So basically, you can put this constraint on the MZ dark epsilon plane of before. But actually, so you see that electroweak precision measurement, so here is the bound of 10 to the minus 3 for the branch ratio. So you see that electroweak precision measurement are still doing better. But actually, so the question is, so we are taking the ZZ star analysis with only 7+8 TV data. So what you can do, first of all, at 14 TV LHC, and what you can do if you optimize the search on these 4 leptons in the case that you have this additional Z dark H boson. And this is actually the work in progress that we are doing now with these collaborators. So our aim is basically to compare the status of electroweak precision measurement and these exotic decays of the Higgs to ZZ dark at the end of the LHC, let's say 300 or 3000 inverse femtobar. So basically what will change at the end of the LHC is that, first of all, there will be some improvement in electroweak precision observables. So looking at this no mass report on electroweak precision measurements, you can see that you can have improvement on the double mass measurement, Higgs measurement, of course. But actually these observables that are mainly improving with LHC are only affected at loop level by this Z dark gauge boson. So we do not expect that this bound will really change if compared to present. But what really will change is the bound on this ZZ dark decay of the Higgs. There have been some projection in this paper that is showing that basically you can expect to have more than 1 order of magnitude of improvement, but simply again using ZZ star type of searches. So what we want to do next is also to try to understand what happens if you consider Z dark and are a little heavier. So basically if you see here, this branch ratio cuts at here, that is like 35 GB or so, when you cannot produce any more on shell the Z dark. But
can you just leave that slide on? I'm confused by the labeling of those curves. So the deepest limit comes from assuming the Higgs to ZZ dark is 10 to the minus 5. Am I reading that?
Yeah, so
10 to the minus 6. I think.
Right. So these curves are.
I would have thought it would be ordered the other way. We might not understand it yet.
So basically these curves are showing what is the branch ratio of the Higgs into ZZ dark in this plane. This is not a bound, this is simply a computation of the branch ratio.
Oh, I see.
Okay? And then actually the bound that we found at the moment is at the level of 10 to the minus 3.
Okay, I misunderstood. Okay.
So it's only here. And the issue is to understand what LHC 14 can do.
Okay.
And we believe that we'll end up somewhere here, between 10 to the minus 4 and 5, if you consider a production of on-shell Z dark. But then again, you have also this region here in which the Z dark will be produced off-shell. And this, so basically what we plan to do is a shape analysis. Basically you have 4 leptons and you can look at invariant masses and try to, discriminate between the Higgs going to ZZ star and the Higgs going to ZZ dark. So this is the plan of this paper that fortunately I don't have too many results to show you, but this is basically the aim that we have, starting to probe all this region here that otherwise would not be probed. Okay, so this is the first model I wanted to speak about. Now if we don't have other questions, let me pass to the second model. So the model is based on this mu minus L tau gauge symmetry. So this gauge symmetry is kind of cute because it's anomaly free. It's one of the few anomaly free. So in principle, you do not need extra matter to cure anomalies. And it has been studied quite a bit in terms of neutrino model building. So how it works? So if you have this symmetry, L mu minus L tau, and you don't break it, so in first approximation, what you get, if you charge the neutrinos under this symmetry, as you do, then you get a theta 2,3 that is maximal, and instead the other two mixing angles that are 0. And then in terms of the masses of the three neutrinos, you get two masses that are degenerate. This will correspond to the mu and tau, basically, and then a third mass that is split. And so this is if the gauge symmetry is not broken. Then if you break, there are plenty of models of breaking of this U1 prime symmetry. Then you will have some effects of for neutrino masses and mixings. So these effects are linear in this symmetry breaking web over the mass of your right-handed neutrinos that are doing C-so. And instead, this is linear in theta 1, 3. And instead you get a quadratic correction to theta 2, 3. And then you get some corrections to these degenerate neutrino masses that then will be split proportionally to this ratio. So basically, numerically, it has been shown in these papers and actually others that you can get the right, mixing and split for neutrinos using this mu minus L tau symmetry. So in this respect, it seems kind of interesting, completely motivated by different things than dark matter. So the issue is how to probe this symmetry. But before letting you know how to probe this symmetry, what I wanted to mention is also the fact that this symmetry can also kind of explain this anomaly that has been published last August in this level transition. So how it works. So what LHCb is measuring is the decay of a B meson to a K star mu mu. So effectively it's a B to S transition. Okay? This is the contribution of the standard model. So they have actually 6 observables that they are measuring, and then they are comparing to the standard model prediction. So this P5 prime is one of these 6 observables. That is a bit difficult angular observable that you can write down using your 2 muons and the pion that is coming from the K star decay actually. So this is an angular observable. And as a function of Q square, where Q square is the invariant mass of the 2 muons, and you see that the low Q square, where actually the standard model prediction is more reliable, you have this kind of 3 sigma-ish or so deviation. So there have been a lot of work on basically 2 different approaches, trying to understand if the standard model is being computed well. If it is a statistical fluctuation, this we cannot know until when we hear more from the LHCb. Basically, we expect that for this summer to have a new result based on the full statistic, so 3 inverse n to 1. And if it is none of these 2, then what about if it is in physics? This is the usual game, right? So in terms of effective operators that you need in order to address this anomaly in flavor, you need these O9 and O9 prime operators. So basically you need a vector coupling with muons, you need some extra particle with a vector-like coupling with muons, and actually an axial vector coupling with quarks. Okay? And this is the Newton scale that you are thinking about if you want to cure this anomaly. So it is a quite high scale. Okay. There's been shown that actually in the most studied models like supersymmetry or composite Higgs models or so, it doesn't work. So you have too much constraint, so it doesn't really work. So a lot of papers have been done in frameworks of Z prime models to try to understand if you can fit it. And what is nice of this mu minus L tau symmetry is that actually, so you have this Z prime that is coupled full strength to muons. Then it won't couple to quarks directly because you are simply gauging mu minus L tau. So basically what you need are some extra mirror fermions that are mixing with the fermions of the quarks of the standard model. But you see that thanks to this mu minus L tau symmetry, basically you can get, actually here there is a typo, sorry, a minus, there is a minus here, so you can get some minus sign in this Wilson coefficient, so it's kind of easy to get the structure of axial vector coupling in the quarks. And if you do that, then you
See,
will...
how does that minus sign give you the axial?
So of course, so these are kind of Yukawa couplings that are mixing these mirror fermions to the quarks of the standard model. Of course, it will depend on the on the sign of these quarks of these Yukawa couplings.
Right.
But the sign here, that again here is a minus, is coming from the charges of these mirror fermions under this Helmholtz of tau. And the if you want to write down this mixing here, the charges of the SU2 doublet have to be opposite than the charge of the SU2 singlet. So basically you get automatically a minus sign here. So this in brief to say that you can get axial vector coupling relatively easy with this choice of charges that you need. But if so basically if you think about this effective Z prime that is coupling also with the quarks of the standard model through this mixing with heavier vector-like fermions, then what you will generate is also some effects in this best mixing. So basically, what you do is to take this part of the diagram to double it, and then here is your new physics effect in this best mixing. If you look at this dependence here, it's the same dependence that you have on these Wilson coefficients here that you are using to address this anomaly. So basically, this is telling you that you have an upper bound on the breaking of this U1 parine symmetry that is at the level of, let's say, 2, 3 TeV. And this upper bound is telling you that also in general you would expect to have a Z prime that is quite light. So basically this is a kind of a model that we brought down such a way to address this anomaly. But then what we got quite interested is to the fact of, okay, we have this Z prime that is coupling only weakly to the quarks, but full strength to muon and taus. How you can probe it kind of model independently, following this motivation if you want. So, since as I said, it doesn't at first order couple to quarks, then you don't imagine to produce it at LHC. You will produce it only weakly. So, of course, the first probe of parameter space that you will have is a probe coming from G-2. You will have a loop effect on G-2. These couplings here are, let's say, of the order 1. So all this region here of parameter space would be excluded by too large effect in G-2. What next? What you have is also an effect on tau decays, actually. So basically, you will affect the width of the tau decay into a muon, but not the width of the tau decay into an electron, through these loop diagrams. And actually, if you put together this new measurement of Bell for the tau lifetime, you see that basically this green region here would be the region favored by the measurement of the tau decay into a muon. So again, this is an additional region that would be probed simply studying physics of taus. And what else? Then we have to remember about electroweak precision observables. Now the main contribution is coming from the fact that you are affecting the coupling of the Z with leptons, so muon and taus and neutrinos, through these one-loop diagrams. If you look at the lab papers, you can see that actually the axial vector coupling of the Z with leptons is measured at the level of 0.1% or so. So actually, as you see here, all this region here and here is constrained by lab measurement of the Z couplings. And so basically, this is all that we got before the LHC. But you see that, so if you think about, we're still thinking about gauge couplings that are of weak strength, and all here you don't have really any probe. But then also there are kind of interesting measurement by the LHC. So what LHC is measuring is this rare decay of the Z boson into 4 leptons. So basically, the measurement that they are making is a measurement that is showing that we have agreement with the standard model. So this would be, this is the measured value for this branch relation, and this is the standard model prediction in this phase case. So basically, you are reconstructing the Z resonance. So you can see from here that you don't have too much room left for additional contribution to Z into 4 leptons. But actually having this Z prime, so Z prime will give an effect because you will have diagrams of this type where here you are replacing the Z star with the Z prime. So basically you will affect the 4 muon beam because the Z prime is only coupling to muon and 1000, not to electrons. So basically what you can do is to recast this atlas analysis and see what is the bound on the coupling of the Z prime with muons and of the Z prime mass coming from this measurement of the rare Z decay into 4 leptons. And this is actually the bound. So all this region here would be excluded by Z to 4 muons. And as you see, basically this interesting measurement of the LHC is telling you that it's very difficult to accommodate G minus 2 with the Z prime that is coupling with muons. And this is very model independent if you want, because you are simply using the fact that the Z prime is coupling with muons. This is giving you effect on G minus 2 and effects here. So this measurement is cool in this sense because a lot of work has been done for Z prime and G minus 2, but it seems that you are quite in trouble. Okay?
So if you allowed it to couple to something in addition to muons like electrons, that just worsens this situation?
For sure it doesn't help. So this atlas search is in 4 leptons, so they use the 4 muon beam, 4 electron beam, and 2 electron to muons. For Z prime coupling only to muons, you have a new physics effect only in the 4 muon beam. The 4 electron and 2 electron to muon beam is measured as well as the 4 muon beam, so I don't expect that it's better to couple it to electrons. So, yeah. And so this is the improvement that we had thanks to the LHC. And but actually, if you remember, so the quite a bit of a motivation of this Newman and Tau models were coming from neutrino physics. So the question is if neutrino experiment can do something here, and in particular for this remaining region of parameter space. And actually there are interesting, quite old neutrino experiments that not too many people know about. So this Charm 2 experiment done at CERN basically 15 years ago or so, way before my time, we're measuring basically this trident production. So what they were doing is to shoot a neutrino against some heavy nuclei, like iron or so, and then look at, in the final state, at 2 muons plus a neutrino. And so the first evidence of this process was observed by Charm 2. So this is the number of events that they observed for this process. Confirmation of this process arrived from CCFR at Fermilab, early 90s. The improvement here is that they were able to confirm the destructive interference between these two diagrams. So basically the standard model cross-section is more or less 60% of the W cross-section because you have destructive interference. So basically, this was a very good test of electroweak interactions. And so these are the number of events and standard model prediction observed by CCFR. And then finally, this process have been also observed finally by NUTEP. going more into the details of the measurement, this is quite a cool measurement because one has also to think of when it was performed. So it was a quite difficult measurement because the cross-section that we are speaking about are cross-sections that are very small, like 5 orders of magnitude or so smaller than the inclusive neutrino nucleus cross-section. And also it was quite difficult to disentangle between your signal and the main background that is coming from charm production, with the charm decaying semi-leptonically. A good discriminant was this invariant mass of the two muons. So basically you see here is the mainly the background that is going to higher values of this invariant mass, and this is the Monte Carlo simulation for the trident. So basically the main trick of this analysis was to require a very, very low invariant mass of the two muons. And so why this trident production is important for us? So it's because if you have this Z prime that is coupling to muons, then you will have also contributions of this type. If the Z prime is not too light, then you can approximate this Feynman diagram as a four-family interaction, so your computation is quite easy. You see that you have always a constructive interference, so basically the Z prime is always enhancing your trident production. But then you have to compare with the cross-section that have been measured at CHAM2, CCFR, and NUTF. And therefore, you see that you are setting this bound in the parameter space, so all this red region would be excluded by this trident measurement.
So this is somehow a sequential Z prime? I mean, you have to make a specific assumption about the couplings in the Z prime.
No, actually, if
interference?
No, because so if you gauge mu minus L tau, right? Then
yeah, that's your assumption.
Right.
Right. Got it.
That's all. I mean,
okay.
There's nothing else.
Yeah, that's your assumption. Right.
Yeah.
Right.
And again, looking at this exclusion here of trident of the trident measurement, you see that again G minus 2 is very, very much in trouble. But if you want, there is a little bit more model dependence here because you're assuming that the Z prime is coupling to muons, to neutrinos. If you remember this Z to 4 lepton bound was, even without that model dependence. So, but still, if you put together Z to 4 muon measurement plus trident production, you see that your G minus 2 is not really working anymore. Okay. It's also quite interesting to see that there are these very old neutrino experiments that are putting these strong bounds, even beyond LHC bounds, and it will be interesting to see if future neutrino experiment can do better than this.
What is that footnote down there about the later NUTF publication?
Yeah, so
What's
this is a
relevance
tricky
of
thing. So there are two papers on NUTF about this. So there is a public note and a paper. The paper comes like a few months after the public note, and the paper doesn't agree with the result of the public note. So in the sense that what the paper is showing is a weaker constraint, quite weaker actually. So that's why here in this plot we are showing, so CCFR is quite solid bound, and this would be this bound here. And we are not sure if this NUTF result is a reliable result.
So, sorry, I lost track. How would it change your plot?
Yeah, so
if it were not?
If you take the published result, this bound will go more towards this line of CCFR. So
Okay.
there will be this small shift
Okay.
here. This is something a bit complicated to understand because it's 15 years ago analysis. So we are trying to speak with the people that were doing this analysis, but it's not really easy to understand what was going on this bound here. That's why there is this footnote here. And as I said, so here we are always showing Z prime gauge bosons of at least like 5 GeV or so. In this case, the computation is pretty easy because you do this four-family interaction approximation. If you go to lower masses, so we wanted to know how this bound bends. And so if G minus 2 can be explained at a certain point for very light Z prime. And but now if the Z prime is very light, you cannot do, of course, anymore this four-Feynman interaction approximation because now the momentum flowing here is large. So you have to do the full 2 to 4 process computation. And there are some tricks. We are doing the computation of the cross-section, putting cuts, and that is quite of amount of work doing this 2 to 4 computation. And the result is that basically, so this blue band here is the band followed by G-2, and so here this red region here is the region excluded by CCFR. I'm not putting nutet here. And you see that basically if you want to explain G-2, basically you have to be like below 300 MeV or so. All the rest, so up here in the parameter space, if the Z prime is a little bit more massive, would be excluded by this trident production. So this leads me to the conclusion. So this is simply a summary of what I was discussing during this talk. So I wanted to discuss with you this kind of well-motivated Z-prime models. One is kinetical mix, one is the mu minus L tau. And the goal is to understand how you can probe the region of parameter space that is left. And in principle, if you can do some cool new measurement either at LHC or future experiment to probe region of parameter space that are left. Yeah.
Okay, thank you. Any further questions? I guess everything is clear.
Yeah, it was quite a bit of fin analysis that we are trying to do to propose new measurements. But yeah, otherwise, I mean, if you think about that, we are speaking always about Z primes that are almost electroweakly coupled and they're very light. So one would like to kind of close the window for this kind of models.
Okay, well, it's thanks to Anya again. I apologize for our experimentalists who